Here's an example of simple linear regression. These here are the observations. So they measured some independent variable, the predictor variable. They then measured the outcome variable and they plotted them on a graph. Then they calculated this line, and that's their regression line. And the line is the same line equation you learned back in algebra. So y equals a plus bx. Typically they go with the Greek letters, so they say y equals alpha plus beta x. This, what they call the residual, that just refers to, for every one of these points that you actually observed, there's some distance to what your line would have predicted. That difference between what you actually got and what your line would predict is the residual. There's some assumptions for simple linear regression. If a paper says they're doing simple linear regression, then they have one independent or predictor variable and one dependent or outcome variable. And they're assuming there's a linear relationship between the two. They're also assuming both x and y are ratio or interval data, and that the pairs of data points are independent, that they're coming from different people. It's not multiple measurements from the same person. And when you're reading the paper, the things you're looking for are r squared, which is always going to be reported in a paper that uses regression. It ranges from 0 to 1, and they'll often say, and they will sometimes say rather, instead of r squared, the percentage of variation in y that is explained by variation in x. They're still talking about r squared. Beta is the slope of the regression line. That's always reported. And beta means, it tells you how much a change of 1 unit in x will change y. And there's no limits on the range of beta. What is often reported, but not always, is a confidence interval for beta. Now, when you're looking at what's a good coefficient of determination, so part of this you can think back to, well, r squared really is our r squared, and the same scale that we used of 0.5 was a good r, so 0.25 is a good r squared. Makes sense. Here you can see some different examples of what r squareds might mean. So if all your scores fall perfectly on a line, then your r squared is 1. If you've got a linear relationship, but it's not a perfect line, your r squared will be between 0 and 1. Statistical significance, so hypothesis testing with regression, we're looking at the slope, the beta. So in correlation, we were looking at the r value. With regression, we're looking at that slope, the beta, and where the p-value is telling us whether that slope that we observed is likely due to chance. A strong p-value is not telling us how strong the relationship is. So you want to see clinical significance for that, right? So clinical significance comes down to how strong is this association? So how big is r squared? And do big changes in x produce big changes in y? So if you think about some intervention, maybe it's recidivism amongst a prison population, and that's your Y output. So the number of people that are likely to wind up back in prison. And your X value is your intervention. So amount of time spent in a halfway house receiving counseling before going back out into the community. What you'd like to see is a big R squared so that you've got a strong prediction, and you'd like to see a steep slope. So you'd like to see that a small increase in the amount of counseling produces a big increase in the likelihood that they're not going to wind up back in prison. If you get a strong relationship, so a big R squared, but your slope is shallow or low, then that means you've got to make big changes in your dosage or your length of time or whatever it is that you're measuring here in order to get a small change in your predictor variable. So when you're reading a paper and it's doing linear regression, you're looking for a strong R squared, so something greater than 0.25, statistical significance, and a steep slope. And units matter here. So what you want to see is if they're measuring units in terms of days or weeks or months, that's if they're measuring units, their change in terms of months, that's a lot different than an intervention change measured in days. You'd like an increase of 1 or 2 days to produce a big change, not a change of 1 or 2 months.